Hello, I'm Betty, a math teacher from South Carolina. I'm here with Judy, a math teacher from Colorado, and we're going to explore the factored form of a quadratic function. You may have studied various forms of a quadratic function in the past. The standard form is shown at the right, the vertex form, with h and k as the vertex, and the factored form of a quadratic function, which we'll explore today. Notice it's written as f of x equals a multiplied by these two factors. To explore this, we're going to use the transformation graphing app on the TI-84. We can only use parameters a, b, and c in this app, so we'll write the equation as shown at the bottom on the right. Judy's going to press the app's key, and you may arrow up or down if you do this, and select transform. And the transformation graphing app will make the y equal entry look a little different. In the TI-84 plus CE, or the TI Smart View software, you can arrow to the left of the Y1 and press enter, and arrow down to Y1 in this screen and choose various preloaded functions. One of the ones that's been preloaded is the factored form, a multiplied by x minus b times x minus c. Judy's going to arrow to OK and choose that. Alternatively, you could simply type this equation in Y1 using your keypad. Now she'll press graph, and the last values stored for a, b, and c will be shown on the screen. Currently, as you see, a is equal to 1, b is equal to 2, and c is equal to 4. This positive a value means the parabola opens up. Judy's going to change the value of a, and we'd like you to think about, as the a value is changed, what happens to the x-intercepts? A could be positive or negative. Of course, a cannot equal to 0. So please pause the video and write down your thoughts about what happens to the x-intercepts as the value of a is changed. Return to the video after you've given your response. Hopefully you noted that even though the parabola may have changed from opening up to opening down as the values were changed, or the shape of the parabola may have changed, the x-intercepts at x equals to 2 and x equals to 4, or 2, 0, and 4, 0, did not change. So again, Judy's showing various values, and even though when it flattens out like that, it's a little bit hard to see, but it still has x-intercepts of 2 and 4. Let's now think about what would happen if the values of b and c were changed. Judy's going to change the value of a back to 1, and now she'll make changes in the values of b and c. And as she does this, think about the following questions. I'll read them for you so that you can watch the graph. As b and c change, how do these changes affect the graph? How do they affect the factored form of the quadratic function? How do these changes affect the zeros of the quadratic function? Please pause the video, write down your responses to these 3 questions, and then return to the video. Let's think about these changes and summarize them. Hopefully you noted, as we look at a summary page, that these values of b and c definitely affected the graph in many ways. We're going to move to the next page in the notes at the right and summarize these changes. The factored form, of course, is still the same except for the values changing. If a stays constantly 1, that would stay the same, but a b value of 4 would make this equation x minus 4, as one of the factors. And also, for example, right now, she has a C value of 8. So a second factor could be x minus 8. So we have our ordered pairs of our x-intercepts also changing. In this screen shown right now, the x-intercepts are 4, 0 and 8, 0. And if we set either of those factors equal to 0 and solved, we would have our values 4 and 8 for the zeros of the quadratic function. So the factored form changed, the x-intercepts changed when R and S changed, and the zeros changed. Now let's give you a problem to think about for a moment. Here's an equation, y equals 2x squared minus 4x minus 6. We'd like you to write this equation in factored form. After you write the equation in factored form, identify the x-intercepts and the zeros of the function, and think about how the graph of the function would look. Please pause the video, write your response, your factored form, your intercepts and zeros, and then return to the video. Judy's going to record what we hope you recorded. Since there's a common term on the right-hand side, 2, that can be factored out of the trinomial on the right and leave x squared minus 2x minus 3. This trinomial can be factored. Y equals 2 multiplied by x minus 3 times x plus 1. You can check your factoring there carefully. And let's think about this. What are the x-intercepts? Well, if we set x minus 3 equal to 0, x would be equal to 3. If you set x plus 1 equal to 0, x would be equal to negative 1. Remember, of course, for the x-intercept, the y value is 0. The factor 2 could not equal to 0. So Judy's going to change the b value to 3 and the c value to negative 1. And to change, you just arrow up or down to move to the value you'd like to change. In this case, the a is changed to 2. She arrowed down to the b is changed to 3, and the c value is negative 1. So we have the graph of the parabola opening up, and the zeros are located at negative 1 and 3. So let's think now about how these zeros might be related to another characteristic of this particular function, the vertex. In the window you see right now, it appears that the vertex may have an x value equal to 1. We could verify that algebraically, but just from observation, it appears to be at approximately x equals to 1. So we're going to move to the next page on the right and think about how the x value of the vertex relates to the zeros of the function. Judy's going to record the zeros for this particular one we just explored. Those zeros are 3 and negative 1. We could also write that, of course, as negative 3 followed by 1. And the x value of the vertex appears to be at x equals to 1. Let's try a couple of more now. We'll look at perhaps an x10 at 3. So she's changing b to 3. And we're going to change the c value to 5. So right now, we have zeros at 3 and 5. Look at the graph and see where you think the location of the vertex would be. It appears that the x value of the vertex is located at 4. As you can see from the tick marks, we have the 3 and 5 as our zeros, and x equals to 4 appears to be the x value of the vertex. Let's change b this time to 1. And we'll change c to 3. b is equal to 1, and c is equal to 3. These are our zeros for this new function. And if the zeros are 1 and 3, where does it look as if the x value of the vertex would be located? So again, we have our zeros of 1 and 3. And as you can see from the graph, it appears that the x value of the vertex is located at 2. To justify this algebraically, you could write the equation and determine the vertex. Let's do one more. Let's do a b value of -1. So Judy's going to change b to -1 by typing that value and pressing enter. And we'll change the c value to 2. In this example, it's a little bit harder to determine the location of the vertex. Clearly not at 0 for x, and clearly not at 1. It seems to be between the two, perhaps at x equals to 1/2. Notice that we have left the a value at 2, so you would be able to write the equations since you know the zeros and algebraically determine the x value of the vertex. Do you see a pattern? The one that's probably the easiest to look at, or the ones that are the easiest to look at, are the two in the middle. If you take 3 and 5, how is 4 related? If you take the zeros 1 and 3, how is the x value of 2 related? And as you may have guessed, and again, you could determine this algebraically, if we add the two zeros, may write them as R and S, as you might see in a textbook. If you add those two zeros together, R plus S divided by 2 gives the location of the vertex x value. And that should make sense if you think about the symmetry of the parabola around the line x equals to the x value of the vertex. Now let's consider another question. If the zeros are the same, what do you think would happen with the graph of this quadratic function? And as Judy is moving the b value to 2, we'll leave the c value at 2. So now that our zeros are the same, what do you observe? It's probably not necessary to pause the video. You can see that this graph appears to be tangent to the x-axis. The zeros are located at the same place. The factors, of course, would be, in this case, with a equal to 2, we would have 2 multiplied by x minus 2 times x minus 2. Let's see what happens if Judy changes a to 1. If the a is a different value, but we leave the two zeros the same, we still have that tangency to the x-axis at this location. And to think about what we just reviewed, if you add the two zeros, 2 plus 2 is 4, divide by 2, that value would be equal to 2, and the x value of the vertex is at x equals to 2. What would happen if these values were different? I'll ask Judy to change b to 3, and then change c to 3. And again, we have tangency to the x-axis, and if you add up those two zeros, 3 and 3 is 6, divide by 2, x equals to 3 is the x value of the vertex. And if you have an 84 available, you might want to try that with different values of your zeros. Now, let's consider a challenge. We'd like for you to write a quadratic function with zeros at -2 and 3. So one zero is at x equals -2, and the other is x equals to 3. Use the factored form, f of x equals a times x minus r times x minus s. And after you've had a chance to write a quadratic function with these zeros, please return to the video and we'll discuss your possible answer. As you noticed, we did not give a value of a. So what could you use? Here is one example. Suppose a were equal to -3, and then we have our factors, x minus the first zero, so we have x minus a -2, multiplied by x minus the second zero, or x minus 3. This could also be written, of course, f of x equals -3 multiplied by x plus 2 times x minus 3. Now, of course, you may not have chosen an a value of -3. Think about other values you could use for a. Is it restricted? So we'd like to challenge you to consider other quadratic functions that have these zeros and write at least one other function in addition to the one that you had possibly already written. There's a related activity to this one, and it's located at education.ti.com. It's called Using Symmetry to Find the Vertex of a Parabola. It's in the 84 Activity Central there, and we hope you might explore this one at a later date. For other videos, please go to the TI Education YouTube channel.